inference is even stronger. That's why 5 minutes later, Christine adopted the idea, right? So we try to model this type of process, how the information propagates through this social network using this intensity function. So you really is going to design some intensity function. So one way to capture the history is using the counting process, right? We are going to use this counting process and design intensity based on this history, this counting process. So since in this particular case, David is the source, so his count, because he initiated the idea, the count is always going to be 1. And then you're going to, for instance, model the adoption of the idea by Jacob. So Jacob at some point is going to adopt this idea, at some point later in time, right? So you try to model the intensity function of Jacob. So Jacob cannot adopt the idea if his parent, Christine or Bob, hasn't adopted the idea. So he has to go through Christine or Bob in order to get the idea. So in order to model the intensity of Jacob, you also need to model something like the connectivity between Jacob and Christine, Jacob and Bob. Likewise, you need to also model the history of Christine and Bob, right? That was the counting process for Christine. Christine may adopt the idea sometime earlier in time, and Bob sometime here, right? Maybe even later than Jacob, because Jacob actually has 2 routes where he can get the idea. It can happen that Jacob get the idea first, then Bob, right? It's possible. It's a random process. So you want to try to describe this random process. So by taking into account these 2 possible routes, information can propagate to Jacob. You get his design, okay? It's based on this particular application domain. You design the intensity function like this. So you first look at the set of nodes that Jacob connected to. So in this particular case, it is Bob and Christine. That's why you have just 2 turns. You can introduce other turns here if you have more nodes there. And then you can either choose, essentially assign this value to non-zero or 0, right? Denoting whether the 2 nodes are connected. Then Jacob essentially is going to look at his parent and see whether the parent has already adopted the idea or not, in this particular case Bob, and then check himself whether he has already got idea. Okay, only these 2 conditions hold together, so the intensity is some value, right? So in this particular case, the history B of Bob is a random process, it's not a parameter, it's a history, right? You already observe it in time. And also this one is the history of Jacob, it's also observed in time, it's not a parameter. So the parameter in this model is really this connectivity matrix, this adjacency matrix. You can make it a weighted adjacency matrix, right? Not just binary 0 to 1, it can be a value. The higher the value, the stronger the influence between a pair of people. In this particular case, if the value is high, then Bob has a very strong influence to Jacob. Bob has the idea, Bob gets the idea, and very quickly, Jacob is likely to also get idea as well, okay, if the value is large. So really in this model, the parameter is these guys, okay, right. So, and here you have 2 times because you have superposition of 2 possible routes that information can propagate. That's why you have these 2 things. So once you have such a model, here I'm just specifying parameterization for Jacob. Of course, you can also have a similar intensity function for Bob, right? In this case, Bob only has 1 parent, so he's going to have just 1 turn, which depends on the history of Sophie. Yeah. Similarly, you can have these intensity function of Sophie and other nodes in the network as well, right? So you essentially have 1 intensity function for each one of these nodes in this social network. Once you have all this collection of intensity function, you can just sample, yeah? Given a particular source node, you can sample this cascade, this spread of information process. So here is sort of equivalent ways of building a sample process. So typically, when we sample this data, we also attach something called observation time window to it, right? So just think about it. If these nodes in this social network they are connected to each other, if you wait long enough, wait for infinite amount of time, the idea will eventually, according to this model, be spread to Jacob. Right? So if you wait for an infinite amount of time, right? If you wait for a shorter amount of time, for instance, just 1 minute, right? And then even there's a possibility that Jacob is going to adopt this idea at some point, but given 1 minute of observation time window, maybe only Sophie is affected in this period. Suppose maybe 10 minutes, right? Only Sophie is going to adopt it. So there are 2 things here, the spreading process and the observation time window, right? So supposedly you're given these 30 minutes of observation time window, right? So you can simulate the process, right? You can simulate the process. So what I'm drawing here, you see the edge length has been changed. So I sort of some of the edge, draw some of the edge to be longer, some of the edge to be shorter. So the length of this edge I draw here is going to be proportional to the actual sample time points. Okay. So suppose Bob has already adopted the idea, and then after in this particular case, how many minutes? 8 minutes. And Jacob is adopting the idea. So these edges sort of corresponding to the time difference. Okay. So you sample the process, you get essentially, if you wait for infinite amount of time, everybody is going to adopt the idea, and these edges going to correspond to the sample time. Okay. But if you're only given 30 minutes of observation time window, so the people actually you see that has been infected is going to just be this collection of 4 people, right? Because Christine is infected in this particular sample at 1:48. It's outside of the observation window, right? So you only see these 4 people. So then you sample again, you get a different, slightly different network. Essentially, the edge of the network is going to be different. But given the fixed observation time window, you see a different set of people getting infected. Okay. So that's what you will get actually. The data you collect in real world is something like this. So although there's a random process, and then the ideal information spreading across this social network. If you wait long enough, everybody probably is going to get an idea. But if you only have limited amount of time, you only see a fraction of people get an idea, right? So that's sort of the thing happening here. So there's another, you can draw another sample, right? You can draw another sample according to the process. You wait for 30 minutes, and this time, these 3 people get infected, right? So you can observe many of them. So you call each one of these collection of nodes and the corresponding time point when they are infected by the particular idea as a cascade. 1 cascade, 2 cascades, 3 cascades. So that's the actual data you actually collect in practice. So in practice, you also collect cascade starting not just from a single node, it can also start from different nodes, right? So if you sort of draw a timeline for each one of these user, and then at some point, one cascade can start from user 1, and you see this set of nodes are being infected, right? At a different time point, you just collect this collection of time. If one node hasn't been infected in this particular observation time window, you just set something like infinite to it, okay? The second cascade is going to start with user 3, and then the 4th cascade is going to start with user 1 again, okay, things like this. Okay, you will collect lots of data. So once you have this amount of data, once you have observed actually this data, the question is whether you can recover the model parameter. Suppose you are using the model like that, on this slide. Suppose you are using a model like this. Can you recover the model parameter in this case, this weighted adjacency matrix? Okay, yeah. You only observe this cascade sample from the process, and it's also something observation within some time window. You want to recover this adjacency matrix. Okay. Now it's a learning problem, right? It's a learning problem, right? Okay. And then this is that process. Similarly, for the second process I talked about, convolution, you have similar problem. You use the process to describe how do you actually, it's a generative model, right? How do you actually sample the cascade or this evolving network from the data, and then there's always parameter in it. So let's just take a look at this example. First, you have information spread, and then Jacob at some point find that the original source, David, is very useful. He creates this link to it, right? So we try to model this process, and the link is going to alter the way information spread. Jacob now is going to get the idea from David very fast, in just 3 minutes. And to describe this process, again, we capture the history using some kind of counting process. In this particular case, when we try to model the evolution network, the counting process is slightly more difficult, more complicated. It's going to, first thing is we are going to represent each one of these events as a triplets. And the first element in the triplet is going to be the destination node, the node which is getting the information. And then the second element is going to be corresponding to the original information source. Okay? And then this is the time when this particular node is retreated. Okay, get idea of things like this. Okay? And then, of course, you also need to represent in this particular case the creation of link. Link is also between a pair of nodes. And then you have the first element in the triplets, which is the target node. And then the second element is going to be essentially the source node, right? And then you also have a particular time point attached to it. So Jacob can retweet the original tweets from any one of his users. You want to keep track of the history of Jacob retweeting every one of his original tweeters, okay? So that's why you need to assign, to model the retweeting behavior of a particular user, Jacob, you actually need a collection of counting process to capture the history, right? So Jacob can retweet himself. Yeah, he just like his own tweets. He keeps retweeting himself. Okay, and then Jacob can retrieve the original tweets from David. That's why you have counting process capturing that history. Similarly, Bob has you will capture that history between Jacob and Bob. So similarly for link creation, yeah, Jacob can create link to potentially every users in the social network. That's why you also maintain some kind of history of which other person that Jacob has linked to. Right? So Jacob, in this particular model, we also assume that it's linked to himself. Okay, and then Jacob can at some point link to David and at some point link to Sophie. Okay, you only need to maintain those history where the actual link is created. Okay, if there's no link between Jacob and Sophie, you don't need to maintain that representation or history. Similarly here, if Jacob has never retweeted from some other people, then you don't need to record the history. So the amount of work or the memory you need is really linear in the number of events. Okay, the additional work. So in this particular case, here comes the parameter, right? When you try to design this intensity function, David trying to generate original tweets with some Poisson process. Then there's this parameter eta in this Poisson process, right? And then when you try to describe the retweeting behavior of Jacob to David, so you're designing something very similar to this idea adoption case, except in this case, you allow multiple events, multiple retweets to happen. That's why you're using something like a Hawkes process here to model some kind of mutual excitation. Okay, the excitation of David's original tweets on Bob, things like this. And then it's going to, if Bob, the parents of this Jacob is tweeting a lot to original tweet from David, and Jacob is more likely to tweet, okay? And then similarly, if Christine is tweeting more often, then Jacob is more likely to tweet. In this particular case, you also have parameters here, connectivity and some additional parameters. You can swap these inference parameter into this adjacency matrix. So again, you have this parameter you want to learn, okay? Yeah. Once you have the parameter, and in the equation, similar, you have parameter, right? And then this is capturing the history of these adjacency matrix. You can observe it. That's no parameter. The parameter here, when you try to do link creation, is this term here, alpha. Essentially, if Jacob retweets the tweet from David a lot, it's more likely that David has a strong, very useful information. Okay, these parameter models are likely that the people will link to David. Okay, this is one parameter, and this is a parameter. It is Jacob's own initiative to explore new connections. Okay? So these are parameters, right? So if you look at these parameterizations, okay, we will look at it later. Okay, yeah, essentially that's it. Okay, so you have this process where you have this adjacency matrix, which is going to evolve over time on top of this network. It's supporting the spread of information. You keep maintaining this history of people retweeting other people, and then that's going to drive the creation of new links, and then the adjacency matrix changes, and then you just have a new information diffusion process. You really just put together all these basic building blocks, and there's a lot of parameters in it. Okay. Yeah, you can simulate it once you have all these parameters. The question is, this is a third example. Again, you have parameter in it. So in this particular case, you have many users, maybe thousands of users, or tens of thousands of users, or even more. You have thousands of items, tens of thousands of items, right? And then you try to describe for each pair of user and item, the intensity function. How likely the sort of temporal behavior of this particular user buying the particular product. Okay. So for instance, Jacob probably is buying books for many times, right? You recall exactly the time points for Jacob. So to describe this temporal behavior, again, you record the history as some kind of counting process, and then you design your intensity function. In this particular case, I'm using the Hawkes process to model the buying behavior user. In some sense, if a user is buying some product very frequently recently, it's more likely he's going to buy it again. Right? It's trying to model that. So again, you have parameter here. Here is the alpha. Essentially, just models how likely the strength of inference, the history of Jacob itself to himself. If Jacob had buy a lot, this particular product or one, then if this parameter is big, that means that the history is going to influence you a lot. Okay, so this is some baseline intensity, which is constant. You also need to learn its parameter. It's just that without the history, without considering history, maybe there's already some likelihood that Jacob is going to buy the particular product. So these are parameters you want to learn. Okay. So if you think about the collection, the entire collection of user and item, you essentially can collect all these parameters, some matrices, right? So this is a matrix of baseline intensity of buying some particular product. This one is a matrix of parameter where how strong is the influence of the history. Okay? So these are collection of parameters. So if you think about it, if you have many users and many products, this matrix is going to be big, right? Huge. It's very similar to the case when you have a recommendation system, right? Collaborative filtering. You also have this big matrix. Right? Very often you don't actually get to observe all pairs of user and item pairs. Right? Sometimes Sophie has never buy maybe tower, yeah? And but you try to deduce some parameter for Christine when he's going to buy a tower or a particular book. Okay? So that means that you actually don't get to, you see I have lots of missing entry here, right? You don't get to observe it, but you want to have a model which is able to actually predict the temporal behavior of Christine buying a particular product he has never experienced before, right? Okay, so you have all these parameters in the model. The question is how you actually learn it. Yeah. If you think about it, sometimes you might actually when you try to learn a parameter, it's actually also equivalent to a problem where the network, yeah, these adjacent matrix, right, or this weight adjacent matrix is missing. Right? You don't get to see it. You only see the cascade spreading on this network, right? You don't get to see the actual network. You want to learn back this network adjacent matrix, right? So you just want to estimate the diffusion network structure, right? So if you look at this model and look at it carefully, somehow in all this design I made for this intensity function, I've made it a linear function of the parameter. Okay, so you here this adjacency matrix or the weighted adjacency matrix, the parameter, intensity function is linear in this, right? Linear in this, and this one captures the history. It's some kind of sufficient statistics of the history. Okay, you can compute it when the history is given to you. So the parameter is linear, right? Okay. So that's why when you try to learn this network, which node is going to influence Jacob, you try to learn is a collection of parameters. I just denoted as W. Right? Jacob can potentially link to Sophie and David directly as well. We don't know, right? So we don't get to see this network. We only see the cascade. We want to learn it back. So you first have this full parameterization. And in the end, somehow after estimation, you want to pull it down to the set of nodes which actually directly influence Jacob. Right? So actually, if you sort of abstract this problem a little bit, okay, and then use this phi ti to denote this history, the sufficient statistics of the history. Okay. So you actually get something like, you can write out the likelihood of the sequence of events generated by Jacob, and you get a likelihood function like this on the top. Okay? Log likelihood. Likelihood is just product together all this. So W, right, times the sufficient statistics. We just mentioned that this intensity function we design is linear in parameter, linear in W. And phi t is going to correspond to all these computing stuff. And then you have linear term, linear term, linear term, linear term. And then in the end, you have this survival function. This is just generic likelihood of sequence observations. And then integrate linear, right? So you can, when you take a log, you will have log of this W times phi T1, right? That's why you have sum over every events you see in Jacob, log linear, yeah? And then you will have log of this term. So it's minus integration of W times phi tau and d tau. So because it's linear, you can pull out W. And I denote integration as my capital this phi t. Okay? So it's still linear, right? So essentially in this optimization problem, You have something like a log linear minus the linear. Right? So the likelihood. So in order to recover this network structure, so what you're going to do is you're going to put a regularization. Okay, then you can use some idea from Convex optimization, right? So this is a problem which is convex in W. In this particular case, maximization is a concave problem. So you want to get a sparse network structure, then you can use some of this idea from Convex optimization and then compressive sensing, whatever, okay, to handle this problem. So you just put something called L1 regularization on the parameter W. So it's essentially just sum together the absolute value of all these entries. Yeah? So you get an optimization problem like this. Okay? Okay. And so this problem is actually well studied in some sense in machine learning literature. Okay? You start from a real world problem of information diffusion, you form this diffusion model, and you see the data, you write out this likelihood. In the end, you write like some nice problem, which is concave in the parameter, and then it's a typical L1 regularized likelihood estimation problem. Right? So you can use some standard algorithm to solve it. Right? So this standard algorithm can be as simple as like this. Okay. So it's called a soft thresholding algorithm. Yeah, it's just an algorithm to solve this convex optimization. That's why it's so nice to have a convex optimization problem. We can have very simple algorithm which if you go for optimum. Right? So this algorithm, soft thresholding algorithm, essentially what you do is you need to pick some learning rate for this algorithm itself, and then it's an iterative algorithm. You start with these counts, iteration counts k equal to 0, right? And you set the upper bound for the number of iterations. And what you do is after you initialize your W, this should be W0, and you're going to update your W in this format. Okay, you're going to take your likelihood function, yeah, and take the gradient of the likelihood function with respect to W. You're going to essentially do something similar to gradient descent, okay, in this particular case. And then compare the gradient, the gradient move the version of the updated parameter to this regularization parameter number you have. Okay, if it's not negative, you're going to keep the value. If it's negative, you're going to chop it to 0. Right? You're going to chop it to 0. This algorithm is that simple, right? So you do almost the same as gradient descent, and but you compare to this regularization parameter. If this updated parameter W is smaller than this regularization parameter, you chop it to 0. Otherwise, you keep it. Okay. So it is essentially gradient descent with projection. Okay. So you just keep doing this. In the end, the algorithm converge, or you just hit the upper bounds of the number of iterations. You stop. Okay. So you get a set of W where some of the entries are 0. Okay? Some of the entries are 0 because of the soft thresholding operation. Right? And then now you can declare that those entries corresponding to non-zero W is going to tell you which actual pair is influencing Jacob, for instance, in this case. Right? So of course, this is just the algorithm for individual node. The way you get entire network is going through essentially solving the problem for each one of these nodes. So it's a process like this. Suppose you have just 4 nodes here, and then at the beginning you don't know the network connectivity. You're just proposing everybody can possibly connect to everybody else, right? And then you're going to run this algorithm, pick one node, run this algorithm, pick this W, run this algorithm, and the results of this optimization is going to give you W, which is sparse. Okay? So some of these parents are just not the influencer. Okay, it's going to prune away essentially some of these edges. This algorithm is going to do something like this, and then you can move to a second node and do this L1 regularized estimation again. It's going to prune away some of the other connections. But you just do it for every node. In the end, you get a network like this. Okay. So although I described this as a sequential procedure, but the optimization problem for each one of these nodes is actually completely decoupled. Okay? So you can parallelize the computation if you have multiple computers. So every one of these problems is simple, just solving such a simple optimization problem. Okay? So but you have a sequence of optimization problem which can be easily parallelized. That's why we don't worry about the size of the network. You have one optimization for each one of these nodes, and then the computational gradient is going to be the key computation here. If you have lots of events or the history, so it's linear in the history to compute this gradient. Yeah.
And then, of course, you can do it parallel. But that is not assuming that you are computing. This node does not depend on the other nodes, on the value of other nodes. Like something that can change, like, I don't know, like whether he has retweet or not, or that value is fixed. Like,
so
you don't have like kind of page rank or something that you need to start changing the values.
Okay, so it's slightly different from page rank, right? Page rank, you have this self-consistent equation, you solve it, you get this value. So the difference here is one reason is because we are dealing with temporal data there, yeah. And somehow the temporal information gives you something nice. You don't need to look at it self-consistently. You only need to look into the future. Right? And if you know about directed graphical model, I don't know how many of you have ever learned directed graphical model. If you want to learn the parameter directed graphical model, if I provide you with the observation for each one is variable, when you try to learn the parameter of directed graphical model, the problem is also going to decouple. Okay, you actually learn the conditional probability table for each one is variable separately. So the situation is actually very similar to here. The learning is in some sense very similar to learning directed graphical model. Yeah. Yeah, it's because we, of course, the second reason is because we designed this intensity function to be like this, and you get nice optimization problem. Yeah, you can think about more complicated one. You may not get as simple as this. Okay. Yeah, but there are many possibilities. Yeah, many more complicated cases you can think about, many more advanced techniques you can use in this setting. Yeah, to make interesting tables. Okay. So if you are from statistical literature background, okay, you can also do something in this context. You can study whether this network is actually recovered. If I provide you with lots of examples, you can actually leverage a lot of results, existing results from this fast recovery literature, from electrical engineering or machine learning or compressed sensing kind of community, to study, like, if I provide you more and more cascades, whether I can actually recover the true network, true diffusion network. Okay, I'm not going to go into the detail, but you will get a set of a condition very similar to the case when you try to estimate Scalable graphical model. Okay, and you can leverage all these results, adapt to this case to analyze it. Something called the sample complexity of recurring this network structure. Right. So you can do something if you're from math or statistically for the community. So what I'm going to show you is something more interesting, maybe the network itself, right? So there are already lots of data sets out there which collect all these cascades, spreading among some kind of social network. There's this one famous data set, Manchester data set, essentially collecting the spread of news across many blocks. Okay, this is just a visualization of some of the hot topics spreading in this social network. For instance, this spike corresponds to a particular piece of information. This lipstick on pig, okay, and then other spike correspond to other information spreading, okay. So, but you can imagine that there are many blocks there, and then once there's a news appearing in one of these blocks, it's going to spread to other blocks. Right? So you see potentially these cascades starting from different blocks and spread to other places. Yeah. So you see many cascades. You again try to estimate this network structure. So this is sort of the result you will get. Okay, some example network. What I have drawn here is something like the thickness of the edge is going to correspond to the weights in this adjacency matrix. Right? If a particular node is influencing the other node strongly, okay, the corresponding edge is going to be large. This is the result of the estimation, by the way. And then you see that actually here is more what kind of this is more maybe just generic, right? So you will have a collection of nodes which are connected to each other, have strong influence with each other, which are more maybe related to technology. Okay, you can actually discover this, and the information or the inference between these blocks are tighter. Yeah, if they're all about technology. Okay, somehow it corresponds back to our intuition, right? So the additional thing you get here is you actually get the quantitative description of the inference between different nodes. Okay? So yesterday, some people asked the question that if you have lots of data, right, what would you do? And your data collected online. So in that case, you can use something called stochastic gradient descent to estimate this network structure as well. I don't know in any one of these earlier lectures we mentioned about stochastic gradient descent, but you can use it to do that. So essentially, if you do that, you can estimate your network online. This is a nice visualization produced by Manuel. And then you actually take all this block data and estimate this network as you see more data sets. So you will see that the initial block structure is connected that way, but at some point there's some news happening that the sort of the diffusion network structure is changing. Okay, so something very nice. This one is corresponding to this famous singer and Winehouse. Okay. So he's a British singer or UK singer, I don't know. Right. So you can do some nice thing like this. Okay. Right. Okay. So what I have just shown you is you get this nice Convex optimization problem where your L1 regularization. So in order to solve the Convex optimization problem, to estimate the parameter of this distribution model, it's really a simple algorithm. Right? You just move your parameter by the gradient, and then compare to the regularization parameter. If it's smaller, the magnitude is smaller than the regularization parameter, chop it to 0. Otherwise, you keep the value. So, but in some of the more complicated case, that algorithm is not going to work. So we will have more complicated scenario. For instance, this particular case, right? Collaborative dynamics. You want to sort of estimate the parameter for each pair of user and items. So you have this collection of parameters, right? If there's lots of users and lots of items, this matrix is going to be big. And then the worst case is some of these users has never bought some of these items, right? You don't actually get to observe the data. How do we actually possibly estimate so many parameters if a particular user have never bought the item, right? It's possible to do this. So you can leverage idea from collaborative filtering to estimate this parameter. Essentially, you would say that although I have this entire matrix of parameter, maybe million by million matrix, but somehow there are some canonical purchasing behavior among people, and this matrix is not going to be full rank. It has some low rank structure. Right? There's some cluster of people's behavior. Okay, so you can put some regularization nuclear norm. Essentially, just look at a singular value decomposition of this matrix and sum together a singular value. Yeah, that quantifies some kind of the sort of the rank or the complexity of the matrix. Okay, you can put a nuclear norm here, nuclear norm here, right? And now you still have Convex optimization problem, but the regularization is more complicated. It's that one. And then the simple, the L1, the soft fractional holding algorithm you see earlier, it's not going to work. So you need more complicated, complex Convex optimization algorithm to make it work. So actually, there's another issue in the estimation problem. When you have millions of data points, and when you try to get very accurate estimation of parameter, we actually have also studied a generic algorithm which can speed up the learning of the entire collection of parameter estimation problem using fine processes. So the problem is this, okay? So all of these optimization problem is concave in W, but there's an issue in it. So essentially the issue is this, okay? So when you look at this optimization problem, it doesn't matter whether you put L1 or some kind of lower nuclear norm here. So the problem is this term, okay? This term is some kind of log of the parameter inside the log, right? Log linear, okay? So if you look at this function log x, so it's some function like this, right? Log of something, okay? So this function is not something called Lipschitz. What it means is as this x value gets close to 0, so the gradient of derivative is getting larger and larger, okay? As you move to here, it can be infinite. So if you look at some of this Convex optimization problem, so the speed of convergence of those algorithms, or if you want to get a particular epsilon closed solution to the true parameter, so that algorithm convergence depends highly on this Lipschitz constant. Okay? If you have something like infinite Lipschitz constant, the convergence is infinitely slow, okay, as you approach here. So the best algorithm you can have, if you just use gradient to estimate your parameter, gradient information to estimate your parameter, it's going to be something like this. If you want to get close to epsilon close to the true parameter you want to estimate, And then if you just use gradient, use this previous algorithm, you need at least this number of iterations. Okay, 1 over epsilon squared number of iterations to get epsilon close to the parameter. Okay? So this is normalized. Suppose you want to get 0.01 close, then this is really 10 to the minus 4 here, right? Okay, so 1 over 10 to the minus 4 is many. Okay, so ideally you want to get 1 over epsilon, yeah, or even log 1 over epsilon. So you have a very fast convergent algorithm. Okay. So I'm going to just briefly talk about algorithm. You can shave off these two here. Okay, you just get 1 over epsilon. Right? So this algorithm is based on this again some idea from Convex optimization. Essentially, what you're going to do is you're going to use something like a differential dual. Okay, you're going to reformulate this problem a little bit. Somehow you reformulate this problem, you will find some structure to help you to solve this problem better. Okay. So you can use something called accelerated gradient algorithm to solve it, and with a faster convergence. So have we got some tutorial in here on accelerated gradient? Should be, right? Okay. Yeah. But here, before you use this accelerated gradient, you actually need to do one manipulation. That's to express this log function using something called a differential dual. So you can essentially express something like this. Okay. So what you want to do is you want to pull out this W times phi star t outside of the log. What's not nice about it is this W is hidden inside the log, right? Then when you try to optimize it, it's going to be affected by these Lipschitz constants in the log. You want to pull it out. So the way you pull it out is introduce this differential dual. Okay. So this log function, log W times phi, is going to be equal to this expression. Okay? This value here is going to be equal to the results of this optimization problem. Okay, in this optimization problem, you're going to essentially express a function value as the result of the optimization problem. Okay, so in this optimization, you have a so-called dual variable mu. Okay, and then essentially you have a mu dual variable times this original parameterization W, and this efficiency is phi, and then you have minus log v here. Okay, minus 1. So you can do this manipulation. Once you do this manipulation, essentially you have pull out this parameter outside the log, and then but you get a new parameter mu here, which is simpler. Okay, so we can make use of that in the algorithm. So essentially, in the end, you put them together, you replace this log function by this optimization problem, and then you have introduced some new random variables, which is the new variables, no random variable. And then you get something kind of, like a setup point optimization problem. You try to still minimize, right, the original parameter W, but now you have this new introduced variable mu. For each one is 20 here, and you try to maximize with respect to this collection of dual variable introduced. Okay, from the original problem, we turn it into some kind of setup point optimization problem. And so in this setup optimization problem, it's going to be linear, completely linear in this parameter, right? So the W and W here. So you only have a simple regularization term there. Okay. So it's also linear in the mu here, and then you have some kind of simple nonlinear function from mu here. Okay. We can actually make use of it. So the way you solve it is something like this. Okay. If you just use gradient information and do gradient descent on this setup point optimization problem, you got something called a proximal gradient algorithm. Okay, so what you do is again iterate the algorithm, very similar to the soft thresholding algorithm. You initialize this W and mu, and you compute the gradient of this guy here. Okay, using the current parameter W and mu, right? And then you move your parameter a little bit. Okay, move your current parameter by this gradient. You move this mu parameter also by the gradient. And then the next thing you do is, for W, you do exactly the soft thresholding algorithm before. Okay? So when you have some kind of objective function with L1 regularization, so you can always do this soft thresholding algorithm. Yeah? So you just move the parameter by the gradient bit and then chop it according to this regularization. So if you have optimization problem for mu here, which with the additional term log here, you can always just do this update. Okay, you first move your parameter by the gradient a little bit and apply this formula. Okay, you get closed form solution in both cases. So the difficulty here, the additional complexity here is you have this additional new parameter here. You also need to update. Okay, so the advantage is this actually allows you to design something called a accelerated gradient. Instead of doing one step of this soft threshold, when you're going to do two steps. Okay, that's the idea of accelerated gradient. So you're going to take this W as your intermediate solution. You're going to compute the gradient again using this intermediate solution, W tilde, and mu tilde. Okay, you're going to compute the gradient using this intermediate W and mu you get, and move the original parameter W and J by this newly computed gradient. Okay, and then apply the same soft thresholding and constable formula for mu. Okay, you do two steps of projected gradient in some sense. But the second step of projected gradient is computed. The gradient is computed using this intermediate tutor. That's the idea of accelerated gradient. So I don't want to go into the detail, but what I want to show you is you can learn something from optimization and design new algorithm for this type of problem, estimation problem. So in the end, actually, you get this. You can formally prove that you get some learning algorithm which has this type of convergence. Yeah, if you want to get epsilon close to your solution, you just need this number of steps. Okay, it's a one order of magnitude speed up. Okay, so in practice you also see this. If you apply this soft thresholding or the proximal gradient algorithm, just do one step of gradient, and then you get this type of convergence in some problem. So if you use this accelerated gradient, you get this convergence. So in practice, you will also see that once you have millions of data points, this second algorithm is much faster. Yeah.
So on the slide before, is the gamma
The step size is, yeah, this one, typically in practice, you set it to some kind of a decaying scheme. Okay, from 1 over t or 1 over square root t. T is the number of iterations. Yeah, you can use the same. The rate is the same. Okay. The rate is the same, and then of course in practice you will set slightly different constant for each one of these. Okay.
How do you choose the constants for the?
Yeah, the constant is difficult to choose. That was a hidden secret in the optimization community. Okay. Yeah. So typically you just choose one with some constant. It will converge, give you decent results, but you want to get the fastest convergence. You actually need to do trial and error. Right? There's no good recipe for this. If you just use first order method, if you use some kind of second order information, Hessian, things like this, then you can possibly get rid of this gamma. Okay. Right. Okay. So in some sense the learning is boring in some sense. Okay. So the learning is you just realize that there's some parameter in your model, right? And somehow when you design this condition intensity function, it's linear in its parameter, and it doesn't matter what condition intensity function you design, it's always the same likelihood function, right? Depending on the context, whether you want to recover a sparse network or you want to estimate this gigantic matrix of parameter, you will either use L1 regularization or the nuclear null regularization, right? Then you need to solve the optimization problem. You leverage tools from the optimization community to design new algorithms in this context. Okay, so you can think about many other things. You can think about distributed algorithm, right? Things like this, yeah, ADMN, other things in this context. But I'm just showing you some examples. Okay, now suppose you already have your parameter. You already estimated your parameter from the data, right? You also have your model. You can simulate the cascade or simulate the behavioral user for patterns of predicate products. Now you want to do some inference prediction task. I call it inference prediction. Maybe predicting whether this particular user is going to buy that predicate product tomorrow or not. Yeah. Maybe you want to predict if I initiate the information in a particular block, is this piece of information going to spread to 1 million people in 1 month or not? Yeah. So if you are able to make accurate prediction for this task, then you can make money. So you can choose the target user more accurately. You can choose the target website more accurately to maximize the influence, things like this. So let me just first talk about a simpler case. When you try to do a recommendation for this particular problem, right? So this problem is prevalent in websites like Last.fm, Amazon, right? And all these online purchasing type of website. So in this particular case, you want to do two things. Once you estimate this gigantic collection of parameters, right? So you have one temporal point process to describe the behavior between each user and pair of products. Okay, even this user have never bought a product before, you get its base intensity mu, you get an alpha to describe the temporal point process. So the question is, you want to essentially get this temporal point, you get a parameter transition for this point process, particular user and item. Okay, you get it. So then you want to make prediction. So the first type of prediction you want to make is, what is the next item to buy, right? What is the next item to buy? Yeah. Then you can actually look at, for instance, you fix particular time. What is the next item the data is going to buy in a week? Okay. So the week, the time is going to be, you put it here. You instantiate the time to be a week. Okay. Right. And then which item is going to buy is the item with the largest intensity. Okay. So the intensity is sort of corresponding to the likelihood this user is going to buy some product. Okay, you're going to search for the particular product with the largest intensity. Okay, once you have the time. So it's just such a problem. Okay? So it's optimizing with respect to this discrete item index. And then another interesting thing that can be done by this point process, but typically cannot be done by other approach based on time series, things like this, is predicting the returning time. Okay, so typically people just make some kind of binary prediction. Right? So here you can actually estimate the expected time this particular user is going to buy the next product. Because you have a generated process for this temporal behavior, you can ask the question, what is the expected number, right? So actually it's just, here it's just computing. So from this intensity function, you can also get a density function, as we discussed before. There's a one-to-one relationship between intensity and density. You compute essentially, this integral is the expected time, okay? Expected time the user is going to buy the product. Okay, you just compute expected time. You can also compute the max, something like this, okay? So this is the return time prediction once you have such a model. It's very easy, it's just computing based on this, yeah? And I want to focus a little bit more on something called inference estimation in information diffusion and inference maximization case. So in that case, you will actually see that you need to leverage some of this idea from computer science, especially randomized algorithm, to speed up the computation. Okay? So there's a rich set of problems in this information diffusion point process modeling sort of field. You can leverage many ideas from many different fields to solve particular application problems. So of course, we get a much better result compared to other methods. If you first estimate this type of collaborative point process and make these next item purchase prediction and then the return time prediction. We have experimented with the things like Last.fm. These type of data sets are available online, by the way. And then you have 1,000 users, 3 albums. You just look at how the listening history of the user to the album. You can hold out some of the activity of some user. You can even hold out some activity of a single user for some of the future event he has, and ask the model and make predictions. So in total, this data set has 20K observed pairs. If you look at all possible user and album combination, it's like 3 million, right? But the actual observation pair of user and item is going to just 20K. There are lots of user and item pairs not observed. You just estimate this low end stuff. You can make prediction for all of them. Okay. So you can predict either the next album to listen to or the time, right? So it's a difficult task. You can compare to some of these models based on discretizing the time. There was tensor method and some kind of collaborative filtering based method. And this approach based on low rank factorization of point processes is getting smallest error in all these cases. So we tried many other data sets. For instance, if you work on the electronic healthcare record data. We can use similar idea. You have, in this case, user is going to correspond to patients, and item is going to correspond to particular disease code. Right? So you just want to see, suppose this particular patient already has some disease. Well, what's the next disease code you will see in the next visits of the patients? Or this patient, is very similar to other patients. He has never visited the hospital before, but when he visits, well, what will be the possible disease, things like this. Okay, you also get much better prediction. So all these data are available online nowadays. Very fortunate. Okay, so let me just focus a little bit more on this inference maximization. Yeah. So in this case, the problem we want to tackle is so you have this information diffusion network, right? So this idea starting from David is going to spread across the network, and it's going to be adopted by people. Suppose you already estimate this network structure and also parameter. The question is, if you are going to put the information in David, can you estimate maybe given a particular time of 1 month, what is the expected number of user that is going to be infected? Because we are getting some kind of probabilistic stochastic model. Right? Every time you can sample from this model, every time you see a slightly different collection of people being infected. Right? So that's why you are interested in this question of the expected number of people that is going to be infected. So here, what you're going to do is you are describing the history of each user by its counting process. And then you sum over, so this is either 0 or 1, right? Because you either adopt the idea or not. And then you sum over all these nodes in the network. So that's the total number of people being infected. Right? So, but that's given a particular history. This one, every time you instantiate this learning process, it's going to a different count. That's why you compute expectation with respect to your model. Okay? So that's the so-called inference function. Okay, according to this model. So you can plug into a different time, maybe 1 week, you can compute the expected number of people being infected. Okay? So once you're able to estimate this so-called inference accurately for each one is source node, S here is the source node. You put a source in David, for instance, and you look at the expected number of people going to be infected in 1 month, for instance. You can also move it to a different source node. For instance, you can also alternatively place this information source in Sophie. Right? So based on the diffusion model, you can also compute the expected number of people going to be infected in a month. So another problem related to this is if you're able to estimate this point very accurately, you are able to actually do this problem, so-called inference maximization. So now you want to make this estimation inference and then try to pick intelligently a set of people to initiate the idea, okay? Such that overall, this collection of information sources can infect more people, okay? You are fixing yourself to a set of nodes, which, for instance, size k, okay? I allow you to pay maybe 10 people to like the idea, right? But the goal is to maximize the spread of information, yeah, within a month, for instance, okay? Yeah, then you have some kind of discrete optimization problem like this. You want to maximize with respect to this set of nodes you pick, such that, so here is a set, so you should sum over all these sources, okay? Something like this. And then, of course, there's another problem, more complicated one, I'm not going to talk about, but just mention here, is something called the source localization. So it's just that very often, ideas spread on this social network, you don't get to see the full cascade. You only see part of it. Right? So maybe you are late in the process. Yeah, you only see part of it. Or in the case of disease spread among people, you don't get to see all the people getting the disease. You only get partial observations. So based on partial observation, you want to figure out who is the information source in the network. So again, you can actually use this journey model we have. You can write out the likelihood of partial cascade and try to find the source which maximizes the partial likelihood. So it's just some kind of inference problem using graphical model, yeah, if you understand that. Okay, so we are going to look at these first two connected problems, inference estimation and maximization. Okay. So how do we actually compute this inference for a particular source node and given particular time? So to estimate its expectation. So Unfortunately, we don't have Markov Monte Carlo, MCMC class here. Right? Otherwise, it would be really simple. Right? So you have a random process or some random variable. Right? You try to estimate expectation. What you will do is you draw a bunch of samples from that corresponding distribution. You use the final sample average to compute it. Right? Similarly, we can do something similar here. The difference is you have more complicated random process. So essentially what you do is for the inference estimation problem, a very simple approach you can think about is exactly using sample and then using final sample average to compute inference. What you do is you already have your parameter of the model, right? You already have the intensity function. You can just simulate from it, right? You can just generate cascades from it. So you, for instance, you want to estimate inference for David, you just instantiate, you just sample many network and fix the observation time window, for instance, to 1 month. You see one cascade like this. You count the number of people being infected. In this particular case, 4 people in total. Right? So you sample another one. So you count the number of people being infected. In this case, 2. And then in the further sample, you just sample again, and then you count the number of people infected, 3. So in the end, you have a bunch of samples, yeah, from this information diffusion model, right? Then the inference of David, the expected inference of David, is going to just be taking the average of these numbers. You just have 4 plus 2 plus 3 divided by 3. It's 3, okay? So it's such a simple process, right? Once you have generated model, the next thing is you can estimate the expectation just using final sample average, okay? So just in this case, the sampling process is slightly more complicated, yeah, according to this diffusion model. So you can move to a different people, right? So now I want to estimate the inference of Bob. So I have this diffusion model I can sample again. I sample this diffusion from Bob. I fix observation every 1 month. I count the number of people that is infected by Bob in 1 month. So in this particular, the first cascade is 4, the second cascade is 2, and then the third cascade is going to be 2. Okay, given this observation window 1 month. So then I counted. I average these counts. I get 2.67. Okay, so this number is smaller than the number I get from David. Okay, so sort of you get an estimate that the Bob is not as influential as David. Okay? So you can do it for Christine. You can do it for Sophie. Okay, then you get an estimate for each person. What is the quantitative definition of inference? Okay, in a particular time window. Okay, so if you change it to a different time window, right? If I change it to 3 months, so the inference for everybody is going to increase, right? You're going to have more nodes which is infected within the time window. So, so this inference estimation problem has a time observation window attached to it. Okay. So let's just think about so this algorithm is very simple. Conceptually, it's very simple. Yeah, at least you can do it. But there's some computational difficulties when you try to use this inference estimation procedure for finding the most influential group, to doing the inference maximization. Now suppose you are able to estimate the inference for each person, right? Bob, Sophie, Davey, and Jacob. Now I ask you, if I ask you to pick one person to give money to like your product, your idea, so which one you should pick? You need to essentially go through each one of these person, right? Compute the inference, and then pick the one with the largest inference. So if you actually go through that procedure, so you want to maximize with respect to the nodes, and then that node has the maximum inference. Okay? If you just want to pick one node, it's still a difficult problem. So what you will find is the computation you will need is essentially this. Okay? It's going to P is going to correspond to the number of cascade you sample. Okay? So you have this random process. You can sample a cascade P times. And then each time you need to compute essentially for each node, right? So you want to get the inference for each node. For David or for Bob or Sophie, right? The node is the size of the network. And then based on the cascade, you want to compute something like whether this particular node is within distance 1 month, for instance. So the edge length I draw here is going to correspond to the time. Right? So you want to do some kind of shortest path algorithm. Find out, for instance, when you try to do this count here, sum over NIT equal to 4. Yeah. So you just want to get all the nodes within distance, maybe 1 month. So that's actually the shortest path algorithm to run there. Yeah, there's some computer science algorithm. You can run it in linear time in the number of nodes and edges. Okay, but you have to run it. So essentially, you sample them and you run a graph, and for each node, you need to do shortest path. So you will get this computation complexity, which is quadratic. Okay, it's square the number of nodes in the network. If you have millions of nodes, then you get million by million computation, right? It's just not possible. Yeah. That's why there are two things: opportunity for you to design smart algorithms if you're a computer science student. The second thing is if you design a smarter algorithm, it will be which is linear in the nodes. It will be drastically faster. Okay, we allow you to do it in practice in places like Facebook or Twitter. Okay, otherwise it's not possible. Right? This naive sample. Okay, so how do we actually do something smarter? Okay, such that you can compute this inference for all the nodes in the network efficiently. Okay, that's the question. Right? Here you can actually leverage the idea from computer science to do it. Okay, so previously when we try to estimate parameters. Idea from operational research, right? Estimate continuous parameters. Now you want to do inference maximization, inference based on this process. You want to use computer science algorithm to do it. Okay, there's a rich set of problems you can work on. Okay? So what algorithm can we use? We can use a randomized algorithm to do it. So the high level idea of this randomized algorithm is since you need to compute lots of shortest paths, yeah. So we can first process the graph a bit, yeah, which is linear the number of nodes and edges. And when we try to find the nodes within distance, maybe 1 month to Bob, it can be done in constant time. Okay? The high level idea is this. You first make a slightly more expensive processing, but still linear the number of nodes. You build some data structure, and afterwards, when you query whether a particular node is within distance, 1 month, for instance, then it's constant time. So you want to do something like this. Okay? Then you can shape off this square factor, okay, to something linear. So you will be linear in the number of nodes in the network, and then linear in the number of samples you draw, something like this. So the algorithm, I'm going to first describe the procedure a bit. So to show the entire proof, this algorithm requires a little bit complicated beyond this. I'm just going to explain the intuition. Okay? So the algorithm is a randomized algorithm for estimating the neighborhood of a node in the network. Suppose you're giving a weighted graph. I want you to estimate the number of nodes within distance t. Okay. So this is a computer science problem. So I give you a weighted graph, and for a particular node, query node, I want you to estimate the number of nodes within distance t. I don't want the exact number. I just want you to give me a high probability estimate. Okay. So that's what I need, because I need to estimate, if I start from this information diffusion source, what is the total number of people going to be infected. So this total number of people going to be infected is actually within a particular distance. Okay? So we're just trying to estimate that. So we're going to use a randomized algorithm to do it. So this randomized algorithm is going to first essentially take one of these particular diffusion graph, yeah, or the cascade, and generates additional set of random numbers for it, okay, to build up some data structure. So what you're going to do is generate something called random labels for each one of these nodes. I'm going to sample some random number from exponential distribution, yeah, and then attach independently. I sample this number, attach this label to each one of these nodes. Okay, so if I sample once, for instance, I start from Bob, I actually travel in the reverse direction. I'm going to travel in the reverse direction of this diffusion graph, okay, this directed graph. Okay. And then find out all these, essentially find out the smallest label encountered by Bob. Okay. So in this case, if I start from Bob, the smallest I encounter is himself. Okay. First, he himself has the smallest one, 0.29. And if I start from Jacob, right, I travel through the reverse direction. So it's somehow there's something wrong with this numbers. Let me just rewrite it. So start from, this is the second label, okay, what will happen in this animation. Let me just see about it. Okay, so what you do is, first you draw these samples, right, from random distribution, exponential distribution, you attach a label to this. First thing you do is you find the smallest, okay, you find the smallest label in the entire network. So that's very easy, you just do a sorting, right? So you sample a bunch of exponential numbers, and attached to each one is node. You sort, you know exactly which label is the smallest. That was Bob. And then starting from Bob, you're going to travel in the backward direction of this graph, and then until the distance is larger than 1 month, you stop. Okay. So as Bob is traveling in this reverse direction, he encounters some node. Now this node is going to record this label of Bob. For instance, in this case, Bob is traveling in the reverse direction. He encounters Sophie and David, and both David and Sophie is going to record the label for Bob. Okay, so this is such an algorithm. And then now you finish the traveling for the Bob, you move to the next smallest label. In this particular case, it's actually the Christine, right? It's going to travel in the reverse direction of this network again, and it's going to encounter some node, which is within distance 1 month. It is going to, essentially this node is going to record the label of Christine, right? And then you move to the third smallest label, yeah? You travel in the reverse direction, and then Bob already has the smallest label, then you only have the label for himself. Now you have recorded the smallest label for each one of this node. So it's such a procedure, okay? So it doesn't seem to make too much sense, but it's such a procedure, very simple, right? You just generate a set of exponential random label attached to each node, and you start from the smallest random label, you travel in the reverse direction until the distance is larger than 1 month. And along the path, you match some node, and you just record this smallest label. So you do it for the, you're going to sample this again. Okay, you're going to sample this again. And you generate another sample. Yeah. So this time, yeah, you sample again, so you get a different set of label for each one of these nodes. And now you do this procedure again, find the smallest label, right? In this particular case, the smallest label is 0.23. You travel in the reverse direction of this graph, and it's going to hit some nodes, and you're going to record the smallest label in those nodes that hit by this backward travel. And you move to the second smallest label here, okay? It's going to travel backwards, and then record this label to it. You do it several times, okay? You build out this data structure, okay? So once you have this data structure, it's essentially, for each one is node, it's a list of random numbers, sampled from exponential distribution. And then one magical formula is this inference of a particular person, given a particular time, 1 month, can be estimated based on this data structure, okay? So for instance, if I want to estimate the inference of David or the Sophie, okay, given 1 month, I'm just going to look at the corresponding list of random numbers for Sophie, okay? I'm going to retrieve these numbers, RSI, suppose you have gone through this exponential sampling for n times, you have n numbers here. You're going to just sum together this bunch of random numbers, and then take the reciprocal and then multiply by n minus 1. Okay? That's going to give you an estimate of the inference of S and T. Okay? Okay? So it's such a magical formula. Okay? So the idea is actually has something to do with the special property of this exponential random variable. If you have something like an ID sample from exponential random variable, and then you compute a minimum, and then that minimum is going to distribute it. Again, there's some kind of exponential random variable, but the parameter of this exponential random variable is going to modify by the size of the random numbers that you're taking minimum over. Okay? If you have 100 random variable, then the minimum of 100 exponentially distributed random variable is going to have a parameter which is 100, for instance. Okay, so this algorithm is making use of that property to design this randomized algorithm. The procedure is simple, but the reasoning behind is quite sophisticated. So you can imagine in other cases you can use other computer science algorithm to do it. So overall, what you do is you still have these need to sample multiple, cascades. But for each one of these cascade, you also have inner randomization. Right? You also need to sample m labels and then estimate its data structure and use this magical formula. So in the end, the overall estimation type of formula for the inference of a particular node is going to be something like this. You average over p cascades, and then with each cascade, you have this formula, n minus 1 over some I 1 to m, this random label. You have a list. Okay? So overall, this algorithm is going to be something like this. It's linear in the number of cascades you sample, linear in the number of random label sets you sample, and then it's going to be linear in the number of nodes and edges. Okay? So depending on how many random labels you get here, so you can suppose it's much smaller than the total number of nodes in the network. You get a huge speed up. Okay? Instead of having an algorithm which is square number of nodes, you get some linear number of nodes. Okay? So you do some extra work, but it's worth it. Okay? That extra work is just linear in the number of nodes, and in the end, you get constant time required. Essentially, computing these formulas on constant time. Okay? So it's such an algorithm. Right? So you can essentially estimate its inference very accurately and very fast for every node in the network. Once you're able to do that, you can do inference maximization. You can pick the node with the largest inference. Okay, that's the sort of our NIPS best paper. Okay, this paper is about that. Right? Okay. So if you look at the performance in practice, it really gives you a huge boost in the speed when you try to actually estimate the inference for every node in the network. So this algorithm, randomized algorithm I'm talking about, is denoted as continuous time inference estimation. Right? And then this naive sampling, just sample and average, find the shortest path and the average without using the sophisticated randomized algorithm. It's going to be just called naive sampling. Right? So here, what I'm plotting here is the run times of each algorithm with respect to the number of nodes in the network. Okay? So if you just use naive sampling, do lots of shortest path computation, and this naive sampling approach can scale up to maybe just 10 to the 4 nodes. Okay? If you set the runtime upper bound 48 hours, and this naive sampling approach is not going to finish. Okay? But if you use this randomized algorithm, you can actually run up to 10 to the 6, okay, millions of nodes network without the difficulty. Okay? So it's less than 2 days. So 2 days is fast in modern standard, by the way. Okay. If you just run an experiment in 1 minute and you think it's too long, it's actually really short. Okay. Yeah. So of course you will get much faster algorithm, and then in the paper we also showed it's much more accurate as well. It's very accurate as well. Okay. So we haven't tried a larger network, but I believe the scaling is nice. You can go to 10 to the 7 or even larger. Okay. And we are only using small clusters. To do some of the trivial parallelization. You can imagine that within the company you can use a larger cluster to compute this random sample. Right? Random sample, in some sense, they are purely parallelizable in this case. Okay, so this is the speed. Of course, if you use this algorithm and apply it to this Manchester data set, you have the network. You try to find out which are the websites or blogs which are the most influential ones. You can also find some meaningful websites. For instance, Dig, right? This is some famous one. So suppose you were trying to find 10 combination of 10 websites which are the most influential jointly. Okay. So what you will find is that you will actually select some of these websites which are obvious. Everyone know about it. Dig, and then Softpedia, and then what other things? PC Word, maybe these are more famous ones. And then there's also some less famous ones. Okay? So it's a combination of highly influential blocks and some less influential blocks, potentially acting as some kind of bridge connecting some community. So you can use it for doing this. So okay, so sort of there was just one particular instance of inference you can do. Right? So depending on the actual prediction task you're interested, the inference procedure can be different. You might need to design it completely in order to scale out the inference. Right? The nice thing is there's many tools in computer science, and diffusion algorithm for graph you can leverage to speed up computation. There's lots of research you can do here. So in the end, I want to briefly just mention about some other possibilities using this unified framework, so point processes. Okay. So so far I've been talking exclusively just about modeling these time points, yeah, temporal information, yeah, the time interval. But if you look at the actual data generated from social network or user behavior, it contains a lot more information. For instance, you have textual information, right? So you have short sentences, maybe the entire blog post, maybe a picture, right? You post it. And maybe some additional audios, right? And then these temporal point process data can come together with other continuous time series as well, right? So it's just many, many different types of information. You can think about combination of these point process modeling framework with other types of data. So one example I'd like to just give here, okay, you also have spatial information, right? I've been talking about temporal information, but there can be spatial information. For instance, when people tweet, you have sometimes you get GPS information, right? And then this is some kind of crime data set. You know exactly what time and what location a particular type of crime has happened, right? So in this case, then you can do something like spatial temporal point process. Yeah. So there are many interesting things you can do. And then in this particular example, I want to talk a little bit more in detail is you try to model temporal dynamics and then document or topic information of the document together. Okay? So if you have some experience in graphical model, or earlier we had this tutorial on non-parametric base, right? Non-parametric method. You can combine this type of temporal modeling with topic modeling of the documents. So essentially what you want to do is you want to, given your streams of documents, for instance, nowadays there's a lot of service like Spinner, right? You can actually get lots of block data and track it over time, right? So you want to extract from these data sets some clusters, which are sort of having some temporal coherent structure and also some particular topic, focus on particular topic. For instance, it might be a story related to NASA spaceship launch, and it's going to happen in a particular small, short time window. So these news is going to excite each other. They're going to influence each other, incite each other, things like this. And then at different point in time, you might have a different story. Okay, there's lots of news published about the story in the block sphere, things like this. You want to extract this topic and also describe the temporal behavior of this topic. Right? So what we have done is something called the Dirichlet-Hawkes process. So you can combine this point process, Hawkes process, with the Dirichlet process, okay, from non-parametric base to jointly model this temporal behavior and textual information. Okay, so I believe that in this non-parametric based tutorial, you've seen some example of a modeling network using non-parametric base or clustering using non-parametric base, discovering feature using non-parametric base. But so far, probably you haven't seen them talking about how do you leverage temporal information, right? So this is one way you can actually use temporal information. Essentially, if you remember a little bit, when you try to run the Dirichlet process, the way you resample the sort of the assignment of an item to a cluster is based on the counts of the cluster, right? If a cluster is already very popular, lots of people assigned to a particular cluster at the table, there's a high probability the new item is going to assign to that cluster. Okay? And then there's always a small probability in this Dirichlet process, a new table, new cluster is going to be created. Okay? So you can actually also use that kind of analogy in this temporal point process setting. Essentially what you're going to do is you're going to look at, instead of counts, you're going to look at intensity for each one of these stories. Okay? Suppose you already have a set of case story in your space. I'm going to look at this set of story. I'm going to look at which story has a high intensity. Yeah? So if it's a recent story, it's a hot topic, that particular story tend to have a high intensity. Okay, so the new item that is arriving is more likely to be in this hot topic. Okay, but there's always some small probability this new item can be completely new story, right? Completely new thing. Okay, so it's very similar to that. Okay, so essentially by doing this, you are able to get two things at a time. So you will be able to extract from these temporal streams of documents, both the topics. Okay? So this is the word count visualization topic. So essentially, within the particular topic, if the word occurs with high probability, you join with a larger symbol. Okay? So you can get topic, for instance, this particular, and also you can get a temporal dynamics. You can get an intensity function for that particular topic. For instance, for this particular story, it's about releasing of a movie, Dark Knight Rises. So the temporal dynamic is sort of spiking, gradually changing up, okay? Because before the actual movie surface, there's already lots of advertising and things like this. Okay, people's interest just climb up. We can get this kind of temporal dynamics. And then, but for some other story extracted from these temporal streams of data, spinner data set is something like this one is NASA space launch. Sort of it has more spiky behavior. Okay, because just at the point of launch, people are more interested in it. It's a hot topic, everybody talks about it. Now afterwards, the interest die out a little bit. Yeah, things like this. So you can also think about combining these temporal point processes with neural nets, deep learning. Okay. So far I've been talking about designing all these intensity function using some meaningful components. Right? For instance, I can design a Poisson process, which the intensity is constant, and the Hawkes process, where the intensity depends on the history. There may be self-correcting process, or sometimes called autoregressive condition duration process, using finance a lot. Okay? So if you think about the trading in the finance, it's again point process. People have these type of thing, autoregressive condition duration process, very popular. Okay? And all this model has some limitations. Essentially, you pick a form, right? You pick a form of the model, and you specify the parameter in the model, right? If the actual data generating process is very different from the model you proposed, no matter how high you learn, you cannot fully recover the information of the data. Right? You just learn the projection of the data to your parametric model. So, and then in some of the applications, you just don't know what is the right temporal point process model to use. You can actually use recurrent neural net to do it. Okay. So the idea, I'm just sketching the high-level idea here. We have a KD paper coming out with a menu for this. So essentially, if you think about what is temporal point process, yeah, what it is when you design intensity, it is just a function, right? Non-negative function. Take your history and output some value. So it's a function over the history. Okay? And then you can just use a recurrent neural nets to capture this sequence of events happening in the past. Okay? So once you have these use these recurrent neural nets, and the history is going to be essentially captured by some kind of embedding, okay, hidden states or hidden variables. Okay, so you're going to using this recurrent neural net to update these hidden states, and based on the hidden state, you're going to generate time and potentially other label as well. Okay, so I'm just briefly scanning this. So we have a paper coming up for this. Okay, so these are two possibilities. You can see that you can significantly extend this point process framework to deal with something more complicated in terms of the modality of the data, and more complicated in terms of the temporal dynamics when you are unknown. Yeah, you don't know the actual form, right? So there are many things you can do. You can also get amazing results. Yeah. So it doesn't matter if your actual data is generated from the Hawkes process or autoregressive condition generation process. If you use recurrent neural nets to parameterize it, you can get a very good fit to the data when you have lots of data for learning. Okay, so I'm not going to go into detail. You can try taxi data, training data, learning data, and medical data. You get best result compared to all these competitors. Okay? So, but let me just recap a little bit. Essentially, what I have presented to you in this tutorial, the first part is easy. Okay, it's just about this intensity function key concept. I think that part is easy, but the second part is more advanced. You see more and more technique from operational research and computer science, or even more advanced deep learning model derivation process being combined with this kind of process to address increasingly complicated problem. But again, you can think need a basic representation for this temporal dynamic. The quantity you use to think about this problem is intensity function. There are several examples. If you understand that meaning, then it's already very useful. Okay, it helps you understand other things as well. So once you have this basic building block, then you can actually build a meaningful model. So what I've shown example is the adoption, just combination of a time-limited point process and the superposition property of this point process. And network evolution combination of, in some sense, the Hawkes process and then the time-limited point process. And this one is just a collection of Hawkes process with low-rank constraint parameters. You can do many interesting things already. So this learning, the nice thing is if your parameter is linear, your intensity is linear in the parameter. Okay, it can still depend nonlinearly in the history. You get this nice Convex optimization problem. You can leverage a huge amount of tools for optimization to solve this problem efficiently. Run the primary beta efficiently when you have even millions of data points. And when you have the parameter, you can, on the model, you can do inference, making some predictions. Okay, depending on the task, the prediction can be easy or difficult. Then again, you need to design algorithms. Okay. In the end, I think this point process is a nice framework, especially when this type of fine resolution temporal data and spatial data are becoming increasingly reliable. Okay? So you need a way to think about how do I actually model this data in very detailed temporal resolution. Okay? Making very accurate prediction and doing some kind of time-sensitive recommendation prediction. Then you need to use this framework to think about it. Okay? And another thing I didn't get to talk about is something called control. Okay, so feedback control, if you are from robotics or from reinforcement learning, right? So essentially you're dealing with a system, right? So you want to actually, for instance, some of these inference tasks, you want to look at the current state of your inference maximization, for instance, and then take into account current feedback, and then redesign your policy a little bit. I didn't talk about. You can also do this. So it's such a nice framework. We also have collected our algorithms, and then in the end, I want to just introduce 3 slides. So it's a nice package, right? C++ package, but I believe this afternoon, Manuel and his collaborators going to I'll give some tutorial about a related package as well, but written in Python, easier to experiment in this case. Okay, if you want to have a high performance, C++ package is also good. So we have this PT pack in GitHub. And my student and I put together this package and collecting some of the algorithms we have before. And you can do a bunch of things. You can instantiate all these basic building blocks of the point process. You can also put them together to get this more complicated information diffusion model, collaborative dynamic model, and learn the parameter. We have already several optimization algorithms included. And this inference task I just mentioned, inference maximization, and we can also visualize the sample on these different point processes. So this is the architecture of the entire package. You have all these processes already defined to you. You can define your own new intensity function with a new process. And then it has a generic simulator, sampling, figuring out what to sample from this point. It doesn't matter what intensity function you have. And then you also have encoded several optimization on stochastic gradient, and proximal gradient, and in some cases you have later probability here, and then some kind of second order information, LDF-GS. Okay, you can do inference and visualization. Yeah, very nice. Okay, this is so much, I think. Yeah. Any questions? Yeah. Okay, so for some of the model, yeah, that's right.
So I have like several questions. First is, have you tried to implement this in industrial framework like Convex or something like that? It would be nice to have this idea of with graph lengths to automatically distribute the data and the computing.
Okay.
That's one
Yeah, using GraphX. No, not yet. Okay. So if you want to design a diffusion package, yeah, you can actually build upon it using this.
So, okay, that was one idea that to linearize the problem and it's easy to scale and solve, but then show us the recurrent nets actually are capturing the non-linearities.
Yeah.
My
So
question
actually, let me just clarify a little bit. Yeah, I'm using a parameterization which is linear. Yeah, my intention is linear in the parameter, but it still captures nonlinear effects because the feature, the phi I define, is actually nonlinear in the history. It's just like when you do exponential family model. Right? The entire exponential family model for distributions, the parameter, in some sense, inside exponential is linear in the sufficient statistics. But you can design sufficient statistics which is quadratic, cubic, things like this. Non-linear and they actually work. Right? So just the parameterization is linear such that you get nice optimization problem. You still capture some sort of non-linearity there. So the nice thing about recurrent neural net is more adaptive to the unknown non-linearity. Right? So that's the advantage. So, but in practice, what you will find is in order to learn well for this recurrent neural net approach, you need a lot more data. Okay, so with just thousands or tens of thousands of data points, this recurrent neural net is not doing better. So we really train with millions of data points. At that point, then you will be better than this parametric model. So especially in the case when this particular parametric model is correct. Okay, so the best you can hope for is to get to the performance of that parametric model. Even if you just do that, you cannot do better. Okay. Yeah.
So when you want to estimate time horizon
Yeah.
or to track time horizon how important is smoothness of the parameter in time? So
Yeah. So in this particular case, the network showed probably we didn't put the regularization across time, right? But you can imagine that you can add additional regularization across time, right? So we have a separate papers about time horizon network. Okay, not about this study. It's actually about time series. So you actually regularize the differences between these parameters across time. You can add that regularization. Potentially, you will get a smoother network. Right?
you need some smoothness, right?
Yeah, that's right. Yeah, that's right. Yeah. So now, in some sense, that when we do stochastic gradient descent, because every time you just update your parameter using small number of data points or a mini batch of data points, the change is not that big if you don't use a big learning rate. So you get some kind of smoothness across time. Yeah. If you don't make such a large step in your gradient. Okay. Any other questions? Okay. Thank you.